In the previous video, we discussed the main idea behind rich getting richer phenomena, and we also discussed the steps that we are going to follow for the implementation. In this video, we are going to start off with the implementation. Okay, so let me import some packages that we're going to need. We are going to need NetworkX. We are going to take random numbers, so we will need random package. We are also going to display the network, so let's import matplotlib. Okay, so let's start our main function. Okay, so if you remember from the previous video, if you remember the outline, if you haven't seen the video, you may go back and see the steps that we are going to follow here. So we require the values of n, m and m naught. N is the total number of users, m is the number of edges that every new node will get attached to, m naught is the number of nodes in the initial network that we will start with. Let's take the value of n from the user. So we can use the function raw input, and in case you are using Python 3.x, you can use input function instead of raw input. So let's use this function raw input and ask the user to enter the value of n. Okay. Alright. Next we need the value of m naught. As I told you, you can initialize m naught to be some 3, 4, 5, whatever you want. Let me take m naught based on n that the user will pass. So I plan to take a random value between 2 because that is the minimum number of nodes that should be there in the initial network, and n divided by 5. Up to n divided by 5, I will choose a random number between 2 to n by 5. So assume n, the user entered n to be 100, then I'll take a random value between 2 and 20. That's how I will start the initial network. In fact, if the user enters a very high value of n, that this might not be a good idea. It's actually better to fix up a value of m naught to be 3, 4 or something. For example, user enters n to be 1000, then your initial network will be between a random number between 2 and 200, right? Okay, it's fine. You can take any value of m naught, and if you remember, the only thing is that m should be less than equal to m naught. So here we will take m to be m naught minus 1. M is equal to m naught minus 1. Okay, and we have to start with an initial network with m naught nodes. So as of now, we haven't even started the graph. So let's start an initial graph with m naught nodes. The condition is that every node should have at least one edge. So I will have a path graph because there every node has at least one edge. You can do any other thing, like you can add the edges one by one, just making sure that every node has one link at least. You can manually add the edges, so it's up to you. I will take a path graph. I'll write nx dot path graph of m naught nodes. Okay. Now to start off, I wish to see how the graph looks like, so that we can see the changes that keep happening to the graph at every timestamp. I'm going to make use of a function display graph that we created in one of the previous videos. So I'm going to just take the function from there and I'll briefly explain it here. I'll not write the function line by line here. So let me call that function display graph. Before that, let me copy it. So this is a function that we created in one of the previous videos. I'm copying it and pasting it here. I'll brief out for the ones who have not seen the previous videos. So what this function is doing, we are passing the graph G that has to be displayed. We are passing I. I is the new node to be added. Okay, and NE is the list of the new edges that are going to be added. So basically at every iteration I plan to call this function display graph, and I also want to display the new edge that got added in this iteration. What did I say? I want to display the new node that got added, and I also want to display the new edges that got added. So I'm going to change the colors of these nodes and edges so that it's nice to see how the new nodes are getting added. For that only I have created this customized function. I'm going to use a circular layout. Okay, so I'll use this function nx.circularLayout g, and since I need to display the colors of the new node and new edges differently, so what I have to do here is that firstly I am putting this condition. Okay, so initially there will be no new node, no new edge. So I and NE will be empty. That is what will happen at the first before any iteration takes place initially, right? So new node will be, so we'll maintain a list of new nodes and we'll maintain a list of new edges. Initially they will be empty, and rest of the nodes, which is all the nodes in the graph, rest of the edges, which is all the edges in the graph. So we require these 4 lists: previous nodes, new node, previous edges, new edges. These 4 lists we need. Okay. In case I and NE are not empty, there are some values in them. What are we going to do is, new node list is going to have I, new edges list is going to have NE, which we passed as a parameter. Rest of the edges will be all the edges, rest of the nodes will be all the nodes minus the new node. Rest of the edges will be all the edges minus new edges. Okay, minus the intersection, right? Minus the common edges basically. Okay, let me explain. So it should take BA and AB to be the same edges, right? So that's why we are deducting those edges. Okay. So then we are displaying. So since you want the graph to be customized, having different nodes having different colors, different edges having different colors, you would have to make use of this function draw network x nodes and draw network x edges. So separately you are calling them. So first function will be to display the existing nodes. Second function will be to display the new nodes, or vice versa. First function will be to display the new edges, and the second function is to display the existing edges. Okay, so look at the parameters quickly. We'll pass the graph G and then the position, okay, that we already created, and the node list that has to be given this particular color, and we are specifying the node color to be green here. Okay, and the existing nodes we are displaying red, new edges we are displaying green, and you can also change the style. I'm displaying the new edges to be dotted so that we can precisely differentiate, and the existing edges we are displaying red. So okay, this was about the displaying part. Now we are calling this function display graph, and okay, so we are calling this function, we need 3 parameters, G, I and NE. So let's pass G here, and I, initially there's nothing, there's no node, and the edges also will be empty. Okay, so let's call this function, let's call main to check the functioning of our existing code. Okay, let's call this file, enter the value of n. I'm going to give 100. Okay, so this is the initial graph. This is the initial graph. As you can see, we had chosen m0 to be random. So this is the number of nodes that the code has chosen. This is the initial graph, and we are going to add the nodes one by one to this graph. I can execute it again to see. Again, this is taking these many nodes initially. It's taking quite good number of nodes initially. I'm sorry. It's taking good number of nodes by chance. Okay, I'm just trying to see whether it gives, yeah. So now it took 1, 2, 3, 4, 5, 6 nodes initially. So it always keeps changing. You can fix it, or you can have the code decide. So this is the initial graph, and we are going to add the nodes to this graph now. Now for adding the nodes, let's create a function. Add nodes. Since we are going to follow Barabasi-Albert model, let me name that accordingly. Barabasi. Okay. We should pass the graph there. Okay, we should pass the value of n, the total number of nodes. We should pass the value of m, that is the number of edges, and it should return the graph. That is what we will be displaying. Okay, so we have to create this function now. Now you see there are m0 nodes into the existing graph already. Okay, so we actually need the value of m0 here, right? Because m0 is the number of nodes already. So I should better pass m0 over here and m0 over here, and let me decide the value of m in the function itself. So I'm removing this and I'm passing g, n and m0, right? Let me decide the value of m here. I'll write m is equal to m0 minus 1. Okay, so we have m0 nodes and we have to add n minus m0 nodes more. So I'll start a loop for every node. For I in range, m0 plus 1 is the next node that is going to be added, and we have to stop at n. So since it is a range function, I'll put n plus 1. Okay, because it excludes the last value. So yeah, this is a loop to add nodes one by one. So we'll add the first node, g dot add node. The node is going to be I. Now we have added the nodes. Now we have to add the edges. If you remember from the previous video, we have to do some pre-processing. So let me do that. And under pre-processing, okay, before that, let me also write add the edges one by one. Okay. Now what is the pre-processing? We need to choose the nodes based on the probabilities, which are based on the degrees. So we need to maintain the degrees. So let me take a dictionary. Degrees is equal to mx dot degree g. Okay, this returns us a dictionary of where the key is the node and the value is the degree. Okay, now we also need to maintain the probabilities which will be based on the degrees. So let me create a dictionary. Node probabilities, spelling is correct, probabilities. Okay, node probabilities is equal to empty dictionary. This is what we are going to create. Now how do we create it? As I told you, the probability of node I is equal to the degree of I divided by the sum of the degrees of all the nodes. So we should better start a loop here to assign the values to this dictionary. So I'll write for each in g dot nodes. Okay, node probabilities for each is going to be degrees. The degrees are there in this dictionary, degrees. Okay, degrees of each will give us the degree of that node, and that should be divided by the sum of all the degrees. Now where are all the degrees? Degrees dot values. If you write degrees dot values, you get a list of all the degrees. We are going to sum them up. Okay, and since we are dividing, let me do the typecasting float. Okay, This should work. So we have now created the dictionary node probabilities. Okay, if you remember from the previous video, now the next step is to create a list, that is cumulative node probabilities. Okay, since we want them to be ordered, I would create a list of lists and not the dictionary. Let me show you how we'll do that. Node probabilities cumulative is equal to a list. Okay, so we have to take the probabilities from this dictionary node probabilities one by one, and based on that we will compute the cumulative probabilities. So at this point, let me start a loop. I'll write for n comma p in node probabilities dot items. Now what do we get here? Node probabilities is a dictionary. Dot items will give us a list of the tuples, and every tuple will have two things, n comma p, that is the node comma the probability. So we are capturing that in n comma p here. Okay, and we have to store the cumulative values in the list of lists, that is node probabilities cumulative here. So let me initialize the probability to be initial probability to be 0. You will understand as I go on. So I am creating a list, temporary list, let me call it temp, that we will be appending to this list. Okay, so initially this list has to have node comma the cumulative probability. So the cumulative probability for the first node is going to be basically 0 plus its own probability. If you remember from the previous example we took in the previous video. So the cumulative probability for the first node is going to be its probability itself. So we are going to add 0 to it. And the cumulative probability for the second node is going to be the cumulative probability for the previous node plus the probability for the current node. So we need to maintain this variable previous. Now this is going to be the list for the first node, and we will append it to the node probabilities cumulative dot append temp, right? And the previous should now be updated. So I'll write previous is equal to previous plus p. Okay, because p was the probability for the current node that we appended. In order to add the edges, we will now create another loop. Okay, that will make use of this cumulative probabilities list. One thing that we have to take care of is an edge that has already been added should not be added again. Okay, so we need to keep a track of the number of edges added. That is one thing. Second thing is we also have to keep track of the edges that have been added. So we need to maintain a list of the edges that we have added for a given node so that we don't repeat the edges. So in case and if you don't keep a track of that, that is if you don't keep a track of the edges that we have already added, we might end up adding the same edge again. So in that case it might happen that some nodes are adding lesser edges than m. Okay, so let me create a list new edges is empty. Okay, here we will store the new edges and number of edges added for this particular node, right, initialized to 0. And in order to check whether the same node the same existing node is not going to be connected again, I'm going to create a list target nodes initialized to 0. I'll show you how these lists are going to be used. Now we have to add the m edges to the new node. So I'll start a loop here. While number of edges added is less than m, what do? We have to choose an existing node based on its probability. For that we need a random number. So I'll take r is equal to random dot uniform, which is going to give me a random value between 0 and 1. You can also use random dot random. You can use that as well. I think just check what is the difference between these two. Random gives a value between 0 and 1, right? Okay. So now, if you remember, the only difference between random and uniform is that in random you don't need to pass any parameter, and it gives you a float value between 0 and 1. And uniform, you can pass the parameters a comma b, where the floating point value that the function will return will be between a and b. So if you want a random floating point value between 0 and 1, you can use uniform with parameters 0 and 1. Okay, so that was about the basics of these functions. Now we have to choose an existing node, okay, based on this R. So if you remember, there is going to be a window which this cumulative probability list will provide us. So we have to check the first node's cumulative probability. If R is less than equal to cumulative probability of the first node, we will stop there. Otherwise, we'll go to the next node. If R is less than equal to the cumulative probability of the second node, we will consider that, else we will go on. So let me start a loop here. While not R is greater than, okay, we need a starting point as well. So let me take a variable here. Previous cumulative is equal to 0. So this is just to create the windows. We need to keep track of the previous node's cumulative probability as well in order to find the window. So I'll write while R is greater than previous cumulative and R is less than equal to node probabilities cumulative of the first node. Okay, so we need to keep a track of the first node as well. K is equal to 0, first node K. And if you remember, node probabilities cumulative is a list of list where every member list has first element as the node and the second element as the cumulative probability. So we will write 1 here, right? So while this doesn't happen, that R is not into that window, we will keep going on with the next element. So in that process, previous cumulative is going to be updated with the cumulative probability of the current node, okay, and K will be incremented, okay. Now whenever it finds a node whose cumulative probability is more than this random number, it will come out of the loop, and when it comes out of the loop, it has found the node that is the target node. So target node, we are taking a variable target node is equal to, now node cumulative probabilities is a list of list, and every list has first element as the node and second element as cumulative probability. Now we need the element here, the node here. So we'll write K and here 0. So we'll get the first element, that is the node. Now we have to check whether this node has already been connected to the new node or not. So for that, wait, there is a spelling mistake. Target. Okay. So we have already maintained this target nodes list, which will contain all the target nodes. So if the new node which we have chosen is already in target nodes, we will continue finding another target node. If the target node is not there in this list, we will add it there, okay. So we will write if target node in this list target nodes, what we'll do, we'll continue, okay. We'll find another target node. Otherwise, this target node is not there in target nodes list, so we will append it there. Target nodes dot append this new node, okay, target node. So basically, if the node that we have chosen is already in the list of nodes that is the target nodes. We'll continue. Continue means we will go back here and m is not incremented, so we'll repeat the whole process up to this point. Okay, and in case the target node is not there in this list, we will do the rest of the processing, that is connecting to this node by using the function g dot add edge. So we are going to add an edge from our node, that is I, to the target node. Okay, target node, right? So the number of edges added will be incremented, number of edges added plus equal to 1. And we also need to keep track of the new edges added because we are going to change their color. So we already maintained a list, new, where is that? New edges. Okay, new edges dot append. We will add this edge, and the edge is basically I comma target node. Okay, so this is the new edge that is added. So we can also keep track of the number of edges added, so that we can check whether at every step we are adding same number of edges or not. Let's check print number of edges added. So we'll just keep a track of the number of edges added, and after that we can display. So this is one iteration over, that is one node added with m edges. So at this point we would like to display the graph with the parameters, 3 parameters, g comma, the new node added is I, the new edges added is where we were keeping track, this list new edges. Okay, alright, so this should return the graph, so I'll return g. So I think this function is done and we can start executing it. Okay, so let's check it. Enter the value of n, let me enter 50. Okay, so this is the initial graph. It has chosen m0 to be 2. I'll close this graph and see, this is what I get. In the first iteration, the new node is getting attached to one existing node. So green is the new node and this dotted line indicates the new edge added. So I'm closing it and I see the second iteration. The next new node is getting attached to one of the existing edges. So here you can see there are 3 existing nodes which are red, and 2 of the nodes have degree 1 and one of the nodes has degree 2. So the node which has degree 2 had more probability of getting attached to the new node, which is precisely what is happening. Having said that, you cannot always be sure that always a node which has high degree will always be connecting. It's just a probabilistic phenomena, right? Because preferential attachment is a probabilistic mechanism. The new node is free to connect to any node in the network, whether it has a high degree or it has just a single edge. However, if a new node has a choice between a degree 2 and a degree 4 node, then degree 4 node will be twice as likely to be connecting to the new node as compared to the node with degree 2. So that's what happens. Now let's check the next iteration. Okay, so the new node is getting attached to a node which has degree 1. Okay, so by chance it got connected to a node with less degree because this is probabilistic. Let's check the next one. So again the node is getting attached to a node with degree 1 because there are very few nodes. Now again the node is getting attached to, by chance, a node with less degree. Let's see the next one. So now this node has chosen an existing node with high degree. Okay, let's check the next one. Again it has chosen the node with high degree. Now it has chosen a node with degree 2. So that keeps happening. But overall, the nodes which have high degree will be connecting more to the new nodes. So you can see here again happening there. Yeah, so it is again getting connected to the node with high degree. So as at each timestamp, the network will not be symmetrical. There will be more edges towards some bunch of nodes. If that was not happening, this network would have been symmetrical, which is not so. So I'll have to keep closing this window 50 times. So let me quickly do that. You can keep observing the behavior. Okay. I should have taken a smaller network. Anyway, so this is the kind of structure that you're getting. So our code is working fine. All right. Now, an important property of the networks that follow Barabasi-Albert model or preferential attachment or rich getting richer phenomena is that the degree distribution follows power law. Okay, that means that the number of nodes with less degree are way too high in number, and the number of nodes with very high degree are very less in number. So that is the sort of property that these networks follow. Let us try to get the degree distribution for this network. We had already created this function for plotting the degree distribution in one of the previous videos. So I'm going to just copy paste from there and I'll briefly explain that. So let me copy paste it. I'll quickly explain this. Okay, so what we are doing here is, since we want to plot the degrees, the distribution of the degrees, we need to get all the degrees. So we are using the function nx.degreeg, which returns a dictionary. We are taking all the values from that dictionary, that is all the degrees. We are storing that in this list. Now out of that list, we are maintaining a list of unique degrees, because what we have to check the number of nodes having a particular degree. So we should know what are the unique degrees, basically the all possible degrees that the nodes have in that network. So that is what will be kept in this list. And then we are sorting this list because we have to plot them. Okay, and we will keep a track of the number of nodes with degree 1, degree 2, degree 3 and so on, where the x-axis will have all possible degrees in sorted order. So we have to maintain a count of degrees for all possible degree in the network. So we have created this list. Now in order to populate this list, we have started this loop. For I in unique degrees, we'll take first element of unique degree and we will check in all degrees how many elements, that is how many nodes have that particular degree. So we'll make use of a function count. So we're writing all degrees dot count I. This will return us the number of nodes having the degree I, and we are appending that to this list count of degrees. Okay, and then we are simply plotting them. So x-axis will have unique degrees, all possible degrees sorted, and y-axis will have the count of degrees, that is count of nodes having that particular degree, and we are displaying them in red color, and this is for labeling and title. That's what is the function about. Okay, let's call this function here I'm sorry. Okay, here in the end, in main, we are calling this function plot degree distribution G. Okay. Okay, so let me ask the user to press enter after getting all the plots, after getting all the graphs. Let's check the functionality. Okay, I'll give say 30. This is initial graph and these are the nodes getting added. I'll have to press this 30 times, and after that we should get the distribution if everything works fine. Okay, I'll press enter now. Okay, this is the distribution that we're getting. So this is sort of power law in the sense that the nodes with less degree are very high in number, and the nodes with very high degree are very less in number. So power law is basically this sort of plot. Since the number of nodes is less, we are not getting it very nicely following power law, but nevertheless it is following that law. If you take a good number of nodes, say some 100 or say 1000, you will get a nice distribution. You can also check that. Let's check that. So let's check. Execute this code for some higher value of n, so that we can see the distribution nicely. So in order that I need not press the I need not close the graph multiple times. I'm going to remove this displaying of the graph from all the places. That's all. Yeah, that's only where we were calling this display graph function. So I've commented that, and let's call this with a higher value of n, say 1000. So okay, 158 edges are getting added at every moment. I think it's a very high number. I think I should fix it on a smaller number there. Okay, this is going on and on because it has to go on for 1000 times. So it's going on and on. It's taking some time. Let's see if it is finished. I'm sorry. So I pressed enter and I got the distribution. So this is following solve power law, as you can see, right? So if you take a log plot of this, you will get a straight line. So that's the whole idea about this. So as I told you, the networks which follow preferential attachment follow power law as well, and that is what we have observed as well. So that was the whole idea behind rich getting richer phenomena. Here we were adding the edges based on the degrees, right? More degree, more probability of getting connected. On the other hand, if you add the edges randomly, what should happen? In that case, you will not get this power law distribution, because there is no preference towards getting attached to a particular node. We are just randomly getting connected to the existing nodes. So in that case, you will not be getting power law. In fact, you will getting a normal distribution. So in the next video, we are going to implement random networks, and we will see the kind of distribution that we obtain.